Hello, hello, hello. Thanks for coming back for another exciting video. Nah, just kidding. Well, educational at least. Um, yeah, the title of this one, choosing a buffer, making a buffer, analyzing a buffer. What is a buffer? Oh yeah, I remember. A buffer is a mixture of a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. What? So if we know the strong acids and the strong bases, we know everything else is everything else that could be an acid or a base is weak. And then if you mix that with some kind of common ion in with that, you have a buffer. But without some examples, it makes no sense. Here are the equations. I call them the buffer equations, Henderson-Hasselbalch equations. Very useful in these cases for quickly comparing pH to pKa with the ratio of A minus. These will be given to you on the exam probably. No, on the third midterm, of course they will be. But they're not necessary, absolutely. They're easily derived from just the definition of what Ka is and what Kb is. But anyways, examples. What if I had a mixture of nitrous acid and lithium nitrite? Or it could be potassium or sodium or rubidium or cesium, or probably barium nitrite would work too. Any spectator positive ion that floats away and minds his own business. Um, yeah, that's called the counter ion that balances out the nitrite to make it a salt to go in the water. Anyways, if it's a spectator, then it floats away, and I have this weak acid and its conjugate base in the water. Or I also say I have the weak acid and its conjugate base in the water, although now the conjugate base here is a common ion not coming from the breakup of this acid, this weak acid, but this nitrite ion is actually coming from, oh yeah, by the way, I have a Ka for that weak acid. That nitrite ion is coming from a salt called I imagine the lithium salt, or potassium, rubidium, sodium, whatever. By the way, the best buffer has about equal amounts of weak acid and conjugate base, or weak base and conjugate acid. So if I imagine a 0.1 molar nitrite, I keep wanting to say nitric because nitric is a weak base. Sorry. Oh geez, nitric is a strong acid which is common, and it wouldn't work. Nitric acid wouldn't work because it's a strong acid. I have to have a weak acid, the nitrite ion and the nitrous acid. Anyways, if I had a tenth of a mole of this and a tenth of a mole of this, or in other words, a tenth of a mole of this and a tenth of a mole of this salt in the same water, the same container, what would be the pH? Well, as you can see, if this amount's equal to this amount's equal to this amount, then this ratio is 1, and conveniently the logarithm function of 1 is 0. And so basically I just take the p function, the negative log, pKa, the negative log of the Ka number, 4.6 to negative 4. That comes out to 3.34-ish. And lo and behold, if your buffer has equal amounts of weak acid and conjugate base, that ratio is 1, and the pH equals the pKa. I could frame this in the language of a titration as well. If I had this weak acid and I titrated it halfway with strong base to make water and an equal amount of NO2, nitrite. So if I canceled half of this and brought it to half of this, so maybe I had 0.2 moles of this to start with, and I created 0.1 moles of this from it. That is the midway point of the titration. That would also allow the pH to equal the pKa. A slightly different example where this nitrous acid, I want to go this way, is a little bit different than the nitrite ion. So what if this is 0.15? What if this is 0.08? Well, then I change this conjugate base to 0.08 and the weak acid to 0.15. This term stays the same, of course, the negative log of the pKa of the negative log of the pKa. But this changes from 0 a little bit. And if this is less than this, then the logarithm comes out negative, and and basically, in essence, reduces the pH a little bit from 3.34ish to 3.06. And you can change this to whatever you want, and with this whatever you want. But the further apart from each other they are, then the less effective the buffer. Another example. Here's a really weird acid. I forget the name of it, honestly. Azide acid. The N3 ion in combo with the hydrogen, HN3, potassium. I think it's azide. I'm going to call it azide, but it's probably wrong. I have to look it up. I'm ashamed. It's not very common. I've never made it. I don't know how it's produced. In any case, the K floats away. Potassium, lithium, sodium, rubidium, cesium, probably barium, strontium, probably if you could find it, also spectator. But this allows it to be a salt in a bottle. Dissolve it in water, and all potassiums dissolve in the water, so that goes into the water like that. And I, once again, have this and this in the water. I have a Ka value for that. I looked it up in the table. And if I had equal amounts of the acid and its conjugate base, then again, this is the same as this. The log of 1 is 0, and I have my pH equal to my pKa, which is the negative log of the Ka value. That looks very, very, very similar to what I just did. Dare I do another one? Might as well. Oh yeah, this is an interesting one. Goodness, I think... Oh, I've forgotten the name of this acid as well. I think it's lactic. No, it could be lactic. I'll have to look that up. No, I don't know. Is it phenol? That might be phenol. No, it's not phenol. Anyways, weak acid. I know it's a weak acid. I have the H there. I have the conjugate base part and the sodium salt of that conjugate base. Acid conjugate base, acid conjugate base. Here we'll notice the one thing with this is that Ka of this weak acid is so small. This is such a weak acid that its conjugate base is a stronger base than the acid that it can be thought of as having had come from. So therefore, I'm going to end up with a basic buffer, which is kind of weird. I have a weak acid and its conjugate base. But again, if this is the same amount as this in the water, or approximately the same amount, then the pH equals a pKa. I'll just say it straight up and take the negative log, and the pH of that buffer comes out greater than 7. So even though I had a weak acid, it was a basic buffer. Or here's a straight up basic buffer because I have ammonia and ammonium chloride. All ammonium salts dissolve in the water. Ammonia, ammonium. Here's my equilibrium. The difference here is I throw water in there. That confuses people sometimes, the weak base. Weak bases interact with the water to make OH minus. And let's see. Oh yeah, I have a Kb for that base. Again, if I have equal amounts of ammonia and ammonium, then my POH PKB equation, I call this the basic form of the buffer equation, has this equal to this, and that's 1 as well, and that's the logarithm of 1 is 0, and so the POH equals the pKa. I could have also used the pH equals pKb, pH equals pKa equation from above, but then I would need the Ka of this, which I have the Kb for this, but I could find the Ka for this. That's Kw over Kb for this. But anyways, I'm not quite done. Don't just stop there. I need to subtract that from 14 to find the pH. And as I expected, it's a basic buffer, 9.25. A basic buffer comprised of the weak base and its conjugate acid. Do I have one more example? I think I have one more example. Oh, well, this is a continuation. Just to say, if I didn't have equal amounts of base and conjugate acid, if these were slightly different, then that ratio is not quite 1. In this case, a little bit more than 1, a little bit more of this than this. And my ratio adjusts, my pH adjusts a little bit. Oh, my POH adjusts away from 4.75 by a teeny bit, and my pH adjusts similarly a teeny bit. Alright, last example. One more example. Yep, one more example. What if I had a weird nitrogen-based, that's a pun, base, it's a weak base, a nitrogen-based base, and it's called trimethylamine. and there's a trimethylammonium bromide. Trimethylammonium, again, the bromine, chlorine, fluorine, iodine, spectators float away, don't do anything, but they help counterbalance the positive ammonium type trimethylammonium. So I can make it a salt and get it in a bottle and weigh it and dissolve it in water. Um, yeah, so here's the weird base and here's its weird conjugate acid. I guess I shouldn't say weird, but it certainly is unusual. I wouldn't see it every day in my stockroom. Alright, and the weak base interacts with water to make a weak base in water, and the conjugate acid, I have the Kb for this base, looked it up in a table somewhere. And so if I had equal parts of the trimethylamine and trimethylammonium, then that ratio would be 1, and the POH equals the pKa, and lo and behold, yeah, that same story. Whew, goodness. Well, thanks for watching, guys, and I will see you in class. Have a good one.